All right, thanks for coming, everyone. We're super excited to have Bonghua with us today to talk about his work. He's a final year PhD student at Berkeley, advised by Professor Michael Jordan and Jintao Zhao. Bonghua's research focuses on statistics and information theory with applications in contract theory, noisy computing, robust statistics, reinforcement learning, large language models, and machine learning systems. He is a recipient of the David Sakerson Memorial Prize for Outstanding PhD Research at Berkeley EECS. So thank you so much, and take it away, Bonghua.
Thank you so much, Natasha, for the kind introduction. And hi, everyone. My name is Bonghua. And today, I'm super excited to be here and introducing my recent work on principled post-training of large language models. So these days, we see large generative models in diverse applications, including but not limited to chatbot, including ChatGPT, Claude, or Gemini, along with different copilots or AI agents that help you write code as Microsoft Copilot or use tools to solve complex tasks like Devin. There are also different image and video generation like models, including DALL-E 3 and also Sora. A key challenge here is actually how we can make those models and techniques more open and accessible so that more people can benefit from those new technologies. So we can do a simple math on how hard it is to ensure those accessibility. So imagine that if we want to combine GPT-4 with Google Search, in that if I come up with a question, like what's the difference between iPhone 15 Pro and Pro Max, instead of asking Google to generate 10 pages that I can browse, I want GPT-4 to read all the pages and then give me a summary of all the results. So to achieve this, the cost will actually be tremendous. So according to simple math, the Google search here will usually be around 8.5 billion query per day. And the cost of GPT, for this case, will around 0.04 per query. So if we do the math, we'll find that cost of combining GPT-4 with Google search is around 300 million. And in contrast, the revenue of Google per day is also around similar value. This means it's quite unaffordable to actually even combine GPT-4 with daily Google search. So my solution and research is around building up strong small models combined with better serving methods that can further reduce the cost. So if we start from serving GPT-4 for Google search, but we replace GPT-4 with some 100x smaller model, but they are still of similar capability, then we'll certainly reduce all the cost. And eventually, if we can combine with a 10x efficient serving methods with our recent work, like caching and model routing, then we can reduce the price to a reasonable price that people can afford for combining search with those model serving. So for today's talk, I'll be focusing mostly on the first part, on how we push the limit of those small models through post-training, where I'll be talking about models which is related to Next Raven 13b and also Starling 7b. So as a brief introduction, Next Raven 13b is actually a model specifically designed for function calling that's even surpassing GPT-4. So function calling is the fundamentals of AI agents, where the target here is we want to supply the model with several tools or functions it can query from. And the user may come with a query saying, like, can I go to the concert in San Francisco I went last time, and then pick up my son along the way. So we expect the model to actually choose the right functions or multiple functions to call to accomplish this user query. So in this case, you might first get the contact of the song and get the location and get the last visited places, and then by sending everything to the navigate function to get the route. So as we can see, this is a very complicated nested call. So for those tasks, we design a Hugging Face benchmark that tries to compare all existing models, and we found that with specifically curated data set and post-training method, we can actually surpass GPT-4, especially in parallel and nested complex function calls. There are also independent route bench from third party, where they show that our model is the only one that gives 0 tool hallucination, compared with GPT-4, which hallucinates 23 out of 800 samples. And as another model of general chat model, we're creating and open sourcing the Starling 7b, which is currently the best 7b chat model according to human evaluation on Chatbot Arena. So on this Chatbot Arena, according to the latest data from March 29th, our model is ranking 14 and surpassing larger proprietary model, including GPT-3.5, Mistral 8x7b, Gemini Pro, and also Llama 2 70b. So the main technique behind this is all from post-training, which is a technique that helps improve the model responses. So essentially, the creation of language model in this case is really composed of 2 steps. The first step is pre-training, that tries to prepare the knowledge and dump Wikipedia, book, archive paper all into the language model. And after this pre-training stage, the language model is able to learn how to complete tasks. So when I ask a question like an iPhone cost, then the model is trying to predict the next most possible token according to the data it has seen from the pre-training stage. But in order for the model to answer the queries and understand the user intention, we really require a second stage of post-training, which teaches the model how to best use the knowledge. So if we ask how much does iPhone cost, in this case by user, we can try to fine-tune the model with post-training so that it can answer in a different flavor. So in this case, we can try to tune that so that it can chat with you and use its internal knowledge to answer the question directly. We can also tune that to a function calling model that uses existing functions to search and then get back to you with some grounded answer. So this kind of steering all happens during post-training stage, where we try to design different chat or different chat interface so that the model can actually respond differently. And during the post-training stage of those small models, we did observe one interesting trade-off, which is on one extreme, we did observe some extractive reasoning capability requirement or groundedness, where we hope the model to have minimal hallucinations. One example here would be navigate with Google Maps, where we hope the model can just select the right tools to use without hallucinating with new tools. On the other hand, we also have abstractive reasoning or creativity, where we hope the model can be helpful and harmless. And one good example here might be write a poem about the moon, where the hallucination here becomes a feature but not bug. So we did observe strong trade-off, especially for small models. So that's why we're decomposing the 2 capabilities, where we create the best function calling model and separately a best 7B chat model for those abstractive reasoning. So in short, we did observe that the post-training helped greatly in improving those reasoning capability. So we start from Mistral 7B, and through post-training technique, we can get Starling 7B, which is much stronger in abstractive reasoning. And on the other hand, we also start with Code Llama 13B, and through different type of post-training, we can get Next River 13B, which is really good in extractive reasoning or reliable tool use that even surpass GPT-4. So for today's talk, I'll be focusing on one of them, the post-training technique here, which is reinforced learning from human feedback that creates the Starling 7B. So essentially, reinforced learning from human feedback is a technique that helps align models with human preferences. And it's also trying to make responses more helpful, honest, and harmless. So I'll start with a formulation and existing issues of both the language model training and RLHF, followed by some Siri-inspired sample-efficient algorithm that we proposed recently, and combined with our recently open-source high-quality preference dataset. So combining both the new algorithm and the new dataset, we're able to create the RLHF pipeline that creates the best 7B chat model to date. So feel free to stop me if you have any clarifying question. Okay, so I'll start with the formulation of language model and RLHF first. Essentially, language model these days can be viewed as a next token predictor, where the idea actually dates back to Claude Shannon in his very first paper in information theory, where he tries to use next letter prediction to compress English content. And a similar idea actually also applies today for the existing language model training paradigm, where instead of trying to predict next letter, we're trying to predict next token, where each token is actually a combination of several letters or a subword. So the language model is trying to predict next token in an autoregressive fashion, where if I send I like as an incomplete sentence to the language model will try to predict the probability of next token according to its training data it has seen, and then sampling from that conditional probability distribution to generate the next token. And then we can further send this I like cat to a language model to autoregressively generate the next token. So these days, large language models are usually coming with much more number of parameters, which really range from 1 billion to several trillion parameters. This includes ChatGPT, Cloud, Gemini, or Llama 2. And essentially, reinforcement learning from human feedback is one of the key ideas that creates very powerful post-training models. And the key idea behind this is in the reinforcement learning stage, where we hope to let the model explore better responses by itself. And the key question here is how do we automatically determine if one of the responses is better than the other, and how do we really accelerate the whole reinforcement learning stage with those automatic evaluation. So to achieve this, the hope is that we can have some reward model that tells you how good your response is given a prompt or a user query. Assuming that we have such a reward model, what we can do is following similar paradigm of traditional reinforcement learning paradigm, where we start from sampling a prompt and send the prompt to a language model, and the language model will be sampling a response so that we have a pair of prompt response, and we send both a pair of prompt response to the reward model, and the reward model will be giving you a scalar reward, indicating how good your response is given the prompt. And we're going to use that reward signal, which might be an imperfect signal from the reward model, to update my language model. So I'll give some more mathematical definitions in the next 2 slides. So essentially, the RTRF stage is really a 2-stage procedure, where in the first stage, we're dealing with reward learning, which can be viewed as an offline contextual bandit problem. Essentially, we start from the collection of the ranking data set, which goes as following. We first sample the prompt or states from a fixed prompt data set that we pre-collected. And after that, we're going to sample responses and multiple responses. In this case, it might be k responses from some joint distribution conditioning on this prompt. Those responses might be written by human or might be written by some different models. After getting a prompt and k responses, we're asking a human or different sources of labeler to actually rank all those responses, so that eventually we get a data set that is composed of a prompt, several responses, and a ranking. And we get IID samples from the whole procedure. So with this, we get a ranking data set. So after this, we can try to learn a proxy reward model that tries to explain human preferences using some different statistical methods. Essentially, we're trying to model the human comparison distribution under a Bradley-Terry-Lewis model, which says if I give you 2 responses, A1, A2, given a prompt S, that the probability of human preferring response A1 over response A2 is actually exponential of the hidden reward signal of that response A1 over exponential of reward of A1 plus exponential of reward of A2. This is a traditional way of modeling human preferences from choice theory. And we are assuming that there exists some ground truth reward R star that can explain human preferences in this case. And it's really averaged over all population of human, so that eventually the whole reward signal can be viewed as an aggregation of human opinions. So after modeling this, we can directly write down the target or loss function with maximum likelihood. Essentially, it's also the cross-entropy loss here, where we just try to write down the negative log likelihood on the empirical distribution and then try to minimize the loss here. So after we get to minimize the whole loss function, we can get a proxy reward model that tries to fit according to the ranking data, that tries to explain how human prefers those responses, prefers response A over response B in this sense. So after this stage, we're getting a proxy reward. And with the proxy reward in hand, we can actually do policy learning, where we try to do online reinforcement learning on top of that, where we still start with a prompt or state that is sampled from existing fixed data set. And in this case, we're generating responses directly from the current language model Pi. And we only generate usually one response according to a single prompt. And then the target here is trying to optimize the language model, which can be viewed as policy in reinforcement learning, to maximize the proxy reward that we learned in the previous stage. So we can also write down the optimization objective, which is essentially trying to maximize the policy Pi, which is my language model. And inside the objective is actually expectation of the reward, where my state is sampled from the prompt data set, and this Pi And this pi is actually the current language model generation. And I want to add one extra note here, that in practice, this is really a reinforcement learning problem, or it should be modeled with Markov decision process, where the action is actually the generation of next token instead of the full responses. But here, for simplicity, I'm focusing on this formulation, where I'm assuming this pi policy is just directly generating all the responses after seeing the prompt. So with this two-stage, that's essentially the formulation of the original RTF framework that works well in practice, especially in those proprietary models like ChatGPT or Claude. But it also comes with different issues. So one issue we face is so-called reward overfitting issue, which is that during the reward learning stage, we found that the reward model can easily overfit after approximately 1 epoch of training. This is independently observed in both the training of InstructGPT and also the training of Llama 2. So essentially, if you write down the loss function like this, which is the cross-entry loss, and you do stochastic gradient descent on top of your data using this loss function, you find that the test loss will first go down within 1 epoch. And after that, the test loss will be exploding. Conditioned on the fact that the preference data set from human is quite expensive to collect. This is a very inefficient way of utilizing the data we collected. And this is also another figure that we conducted with real-world experiments, where we observed similar phenomenon where the model, where the model first goes down in test loss, but then the test loss drastically goes up. Question?
So are we asking for the full ranking from each specific person?
Exactly. So,
and then that presumably has like n squared comparisons in it?
Yes.
Okay. Yeah.
Yes. And for this phenomenon, it's even happening even if we only have pairwise comparison. Any other question? Okay. So the second issue we're facing is in the policy learning stage. So after we finish training the proxy reward, and we will try to maximize the proxy reward, we found that if you maximize the proxy reward too much, it actually decreases the ground truth reward, or GOAT reward. This is also referred to as Goodhart's law, which says like when a measure becomes a target, then the measure won't become a very good measure. So essentially, if we do the policy optimization by maximizing according to the proxy reward, R theta hat, then you find that, as expected, the proxy reward will keep going up with more policy training steps. But then the ground truth reward from either human perception or from some hidden real ground truth signal will first go up and then go down, meaning that we have to do very early stopping in order to train a language model that does really well. There are also some practical experiments which shows that this phenomenon is especially worse when the reward model size is smaller. And still, the dotted line, which is a proxy reward, can still keep going up during the whole training procedure. There are also third and last issue with this ILTRAF pipeline, especially in, question?
Is the ground truth available during training, or is this only through like great extra expense that you can observe this phenomenon?
So in this experiment, what people did is that they assume there exists some ground truth reward. They use that to sample and label like some simulation reward data set, and they get to reproduce this phenomenon. So in that case, the ground truth reward is a hypothetical reward that exists. And people also observe that in practice, like if you just train according to a proxy reward that you learn from data, then the language model real performance will also be going through the similar procedure where it first go up, then go down by human evaluation. Okay, so the third issue related to this is especially an issue in open source community prior to like our starting work, which is that if you go with ILTRAF with a prior open source preference data set and you run the whole ILTRAF procedure, you find that for a learned proxy reward, it will be still going up. But then during the policy learning phase, the real performance from human evaluation will go straight down. So this seems to suggest that ILTRAF is not really helpful, especially when we deal with those open source data sets. But the key issue with that, when you look at those data sets, is that those data sets usually don't have very good data quality So one example here might be, a question is how do I make a fake vaccine card? But both responses fail to understand what is fake vaccine card. So in that case, even when humans try to label those responses according to the preferences, it won't provide too much information about how good or how to improve your model further. So this does call for a high-quality preference data set. So for the talk today, I'll be discussing how we resolve all the three issues, and I'll start with this reward over-optimization issue at the beginning. So essentially, we're trying to attribute this over-optimization issue to the coverage issue in the ranking data set. So when tuning the language model with policy gradient, we found that the language model generated responses can easily get out of distribution compared with those ranking data. So here's one example that we really encounter in practical training. You might start with a very simple problem, like how are you? And when we collect samples by sampling from the current language model to generate those responses, you might get one response that says good. But you might also get some strange response that is a repetition of good followed by some random characters. This is because first, we are tuning the model too much so that the weights are not controllable in some sense. And also, since language model generation is a sampling procedure, we inevitably see some of the strange generation from those language models. And eventually, from human perspective, we always think like response 1 is better. But in terms of proxy reward, when we ask the learned reward model which one is better, it's likely that sometimes the reward would prefer response 2 over response 1. So with this set, what will happen in this over-optimization issue is that at the beginning, when we don't tune the language model too much, most of the generated responses are actually in distribution. And the proxy reward is accurate and very correlated with the ground truth reward. And that's why we see both ground truth reward and proxy reward to be going up. But as we further tune the language model, we find that generated responses might be easily getting out of distribution, and the proxy reward might be inaccurate in this case, and not anymore correlated with those ground truth reward. So this is where the language model performance or the ground truth reward will be keep going down. To mitigate this issue, we need to deal with this out of distribution issue like seriously. So essentially, we can try to leverage some insights from theory, especially in the principle of pessimism, to actually provide some guidance on how we can fix this. So consider a simple setting where we are trying to only have 2 responses, and then we're trying to determine which response has a high reward, especially a true expected reward. But due to the uneven or unbalanced training data, for one of the green response, we have 5 samples. And for the blue one, we only have 2 samples. And in this case, we're getting unlucky so that the empirical mean reward of the blue one is actually higher than the orange one. So as a result, if you just make decisions by taking the best response according to the empirical mean reward or the maximum likelihood estimated reward, it will tend to choose the actions with larger variance. We also have some more detailed analysis for the tabular MTP case in a separate paper. And what we can do here is, rather than directly making decisions according to the empirical mean reward, we try to penalize that according to how confident we are about those estimations. So what we can do is subtract the length of the confidence interval for those estimations, so that in the orange case, since we have so many samples, the length of the confidence interval will be much shorter than the blue case, where we have much less samples. So when you penalize according to this confidence length and make decisions according to this lower confidence bound, you'll find that we're eventually making decisions and choosing the orange one, which strike a balance between how confident I am about the estimation and also about how good the real performance is, or the real reward is for those responses. So we can also adapt this idea to the RTREF procedure. We're assuming we have a linear reward family. What we can do here is we first construct a confidence set that tells me how confident I am about all the parameters here. And then we try to construct the pessimistic reward function rather than the maximum likelihood estimator by introducing a minimizer here. And eventually, it has a closed form solution that allows to subtract in the original reward function a new quantity that quantifies how confident I am about my reward estimation. And eventually, we're going to find the greedy policy with respect to this pessimistic reward function. So we can also show some theoretical analysis and guarantees for this pessimistic MLE idea. So if we assume that the data covers the target policy well, and under this assumption, we can show that for any linear reward and any number of samples, there always exists some instance such that with probability at least 1 minus delta, the greedy policy with respect to this MLE reward will be always lower bounded by 0.1, meaning that no matter how many data you have, you probably won't be getting a reward, a policy that is as good as the target policy. On the other hand, we can show that the pessimistic MLE actually gives you a tight rate into both the dependency on C pi star and the dependency on dimension and number of samples. And as I have more samples, the policy, the pessimistic policy does converge to the target policy. This shows a gap between the original MLE reward and the pessimistic reward. And in general, when we have those confidence intervals at hand, it's good to have those pessimistic MLE reward to actually do the correction. Question?
How practical is this to assume that the data covers the target policy well? Because it seems like when you're learning a policy with a lower confidence bound, it seems like there's going to, in practice, be regions that you're just never going to learn. Whereas it seems better to, at the reward learning stage, to use something like an upper confidence bound to explore more and to just come up with a better reward, proxy reward function. And it seems like this is a very pessimistic and impractical approach.
Exactly. So that's a very good question and comment. So essentially, the reason that we hope to still introduce some pessimism is that we always need to use a fixed reward model to actually do policy training and until the model saturates in the policy learning phase. So we always inevitably go through this model performance going down, and we just hope to increase that in a single run.
I guess what I mean, though, is that from the perspective of actually getting this to actually help, it seems like one could use something like UCB during the proxy reward learning stage, and realize, okay, I've got a reward function that's problematic, and trying to improve that, rather than to show what you shouldn't do when you have a bad proxy reward function.
Exactly. So these are two directions that people have also been working on. So for this UCB idea of further improving your reward in active setting, that's very helpful when you actually have the power to query human again and again using some active learning procedure. And this is also used in multi-round RLHF procedure. But here, since we're working mostly with a fixed data set, given that having human access and query is actually taking quite a long time and quite costly, so we're mostly working on fixed data set. So that's why in the single stage of RLHF, we're mostly working on this setting at this point. Yeah, but in the future, it's definitely very interesting to explore different reward exploration opportunity. Yeah. Okay. So essentially, one good news about this pessimism idea is that it always comes with provable guarantees with minimax optimal rate. But one of the biggest issues with that is that it's really very hard to get tight confidence bounds for this reward learning, especially with neural networks. So the key question here is, can we design any approximate algorithm that can really work for this real-world reward learning procedure? So before I go to this question, I also briefly mention why we're facing this reward overfitting issue and how we can solve both of them simultaneously, assuming that pessimism can be a temporary fix for this reward over-optimization issue. So essentially, we're trying to attribute this cause of this overfitting issue to the unbalanced, noisy training data. So previously, we were saying when we have unbalanced training data set, it might lead to some over-optimization issue that might require some pessimism for single-round RLHF. But on the other hand, it might also lead to this overfitting issue that might require some regularization. So by this, I mean the following. So let's consider a scenario where we compare A and B 100 times, among which A wins B 90 times, and I only compare C and D 1 time. And in this case, C wins D. So essentially, we can write down the loss function here, and we find that the loss in the red part is actually monotone in the reward difference between C and D. As a result, if you do SGD or any gradient descent method, the maximum likelihood estimator where the minimizer converges to might lead to exploding test loss, because where the reward difference between C and D might be going to infinity. This calls for some regularization for my reward model learning procedure. Where the first idea is always we can do early stopping at the first epoch, or different other regularization methods that can try to ensure the reward difference between C and D won't be too large and won't be really being much larger or dominating the reward difference between A and B. So this is exactly what people did in practice, where we try to early stop at first epoch and call that our reward model. But can we do better, given that at first epoch, the model is still not trained quite well? So here comes the second idea. Maybe we can update the label for the comparison using the model prediction after one epoch, or assuming that the model after one epoch is already good enough. Suppose that we originally start with sequencing one time out of one comparison, then we can probably update CD comparison to be 0.5 times. In that case, the loss function will be more well-shaped. And I want to add one remark here, that in practice, we're not really operating with tabular case like this, where we're mostly operating with high-dimensional spaces, where this C and D comparison can be viewed as a comparison along certain direction. And there are always some directions that are compared more, some directions that are compared less. So in this case, we can utilize the insights to design a soft labeling idea. Essentially, we try to design a soft cross-entry loss by introducing a yi and y subtract yi on top of all the data labels. And beginning, we start with yi all equals 1, since we know that that's the labeling procedure from the human. And as we further update the model, we're trying to iteratively update the model with the data using the standard SGD, and also update the data prediction with the model prediction, so that we're moving the data and making it soft. So why it works? I can give you some very brief explanation in the next 2 slides. So essentially, we can start from vanilla SGD, where we know that the initial reward model might be giving similar reward for those frequently observed comparisons and those rarely observed comparisons. And I know that the conversion point of MLE with original data won't be too good, because it might be overly credit those rewards for those rarely observed comparisons, and that would not be a good story according to our pessimism theorem. So vanilla SGD is just trying to move the reward model directly to the MLE. But at the beginning, since we have so many data for the frequently observed comparisons, their gradient is really larger than those rarely observed comparisons. That's why it's moving along this direction that penalizes those really observed comparisons and encourages those frequently observed comparisons. But as you further optimize your model, it might converge to a bad point. So the insights of this iterative data smoothing idea is actually trying to move both data and model to a good position so that they can converge to a better position. Essentially, we still have the initial reward model here and MLE here. But rather than simply moving only the reward model, we can try to move both the MLE data, which essentially move the convergent point, and also move the reward model, so that they can meet in somewhere where the frequently observed comparisons usually have a much higher reward than those really observed comparisons. So we also have some theorem in the paper showing that the reward for these frequently observed comparisons does not change, whereas the reward for those really observed comparisons can be penalized. This is essentially utilizing insights from pessimism, where if you have fewer observations for those data, it really leads to a smaller reward. So with these insights, we're able to get some good experimental results with Anthropic HH preference dataset, where in the reward learning procedure, we observe that this iterative data smoothing enables continuous training of those reward models for more than one epoch, while this original MLE will just keep making the accuracy decreasing and keep the loss exploding. And furthermore, when we use the resulting reward model to train a language model, we also observe that this data smoothing idea is actually keep improving this ground truth reward and until a very high reward point, or this MLE will easily go over optimization when we tune the language model. So essentially, for both overfitting and over optimization, we tend to attribute them to unbalanced training data set. And as a solution, we're proposing this iterative data smoothing idea that somehow covers both overfitting and over-optimization through either regularization and pessimism. But now we're going to talk about the third issue, which is this open source data quality. And the insight from theory is telling us that, especially the pessimism theory, is suggesting that if you have very good coverage of your data set, that can also lead to less over-optimization. So one effort of doing this is actually ensure your data is having a very good coverage so that you don't need to worry about algorithm too much. So essentially what we are trying to do here is trying to ensure both the prompt and responses are as diverse as possible. So we're collecting most of the existing prompts at that time on the internet and sample them according to some criteria. After that, we're going to distill multiple models' responses, including GPT-4, Claude, Llama 2, and Mistral, like that spans from both very strong proprietary models to slightly weaker open source models. And as a result, we're getting a data set with each prompt combined with 7 responses. And then we're asking GPT-4 to give us a proper ranking according to how helpful and how harmless those responses are. So this gives us around 200K prompts with 7 responses each, which results in around 4 million pairwise comparisons. And we open source the data set so that everyone can access and train your reward model with the existing data set. And during the data set collection procedure, we did find that the GPT-4-based ranking procedure can have very serious positional bias. So I'm posting the winning position in the x-axis, where for all the 7 responses, we found that if we directly ask GPT-4 to rank them, the probability of picking the first and second response is much higher than the probability of picking the rest of them. This is quite unideal, given that we do hope that when the responses are randomized enough, the GPT-4 should be really giving uniform probability of picking those responses. We also found that simply adding chain of thought won't be helpful for those cases. So what we did here is we first asked GPT-4 to provide a grounding for those pairwise comparisons, and then summarize with K rankings. And we also incurred those randomized type breaking during the prompts, so that after combining this pairwise grounding and this random type breaking, we did find that it makes the positional bias much less significant, and the data distribution is more even. Question?
So you're calling this bias, but do you know sort of like whether this is not representative of sort of what it learned in training, right? So like it's not obvious to me that like it's not distribution matching, and that maybe the most likely thing is really 30% happening in 30% of the training data or something.
Oh, so essentially one philosophy we impose here is we first randomize all the responses so that they're first shuffled before we send that to GPT-4. So ideally, like GPT-4 should really not have any preference for those that are appearing first, because ideally we want a preference to be uniformly over.
These are positional in a text response. These are
Yes,
not the highest probability.
Yeah, sorry.
Oh,
Yeah,
okay.
this X index is actually the position for winning position in the responses, where we put first response in the first place, etc. Yeah. Okay. So now we are essentially showing that this new Nectar data set, on one hand, we're trying to make it make the coverage as good as possible so that it can deal with over-optimization. And on the other hand, it's also trying to come with better responses so that the open source data quality can be improved. Now we can combine both the new algorithm with the new data set. Essentially, this creates our Starling 7B model, where we also get to benchmark those reward learning algorithms on our own Ultraf data set. So essentially, we find that when combining with this iterative data smoothing idea, this enables much lower loss in terms of both GPT-4 labeled ranking and also human labeled ranking in the reward learning stage. And also, when we use the resulting language model to tune resulting reward model to tune the language model, we observe higher MT bench score, which is a language model-based judgment, where the new model actually has a higher score than the original reward model with MLE. Question?
What is loss here? Is it 0-1 loss?
So it's cross-entry loss that we use to train those reward model. And we're holding a test set so that we're inspecting those test loss in this case.
Clear how I should interpret those numbers?
So it's mostly cross-entry loss in binary selection scenario. And so usually we did observe that small difference in those losses can really lead to very large difference in downstream like policy learning procedure. Okay. So in short, our resulting model is also topping various leaderboard, including Wild-Bench from like AI2, and also Chatbot Arena in ARM6, and also one of the like new leaderboards that will be soon releasing using like Elm as a charge. And so as a result, our model is really dedicated to promote open source dataset, model, and software, where we're gaining more than 2K likes and millions of downloads in 4 months of releasing. One question?
Sorry. Just a question on the leaderboards. My guess is that if you moved all of the commercial sites that were on the leaderboard, you would be higher?
Oh, sorry, I should be going. You mean like the proprietary model?
Academic labs and how many companies that have 10,000 A100s are on the leaderboard?
I think that's a very good question. So I think most of the models here are going through both pre-training and post-training stage. And our focus is only on post-training. So most of the models on top of us are actually from like companies that are really having thousands of GPUs.
Compared to academia, you would be probably higher.
Yes, so maybe then you probably want to remove everything above that in some sense. Yeah. Okay. So essentially, we're gaining like, we're becoming the top training models and data sets on Hugging Face. We also get different supports from both Hugging Face, Meta, like open source community, and there are also different YouTube videos telling people how to deploy our 7B model across devices. So in terms of my future research, I do hope to build up theoretical foundations for democratizing generative models, where my prior work is mostly working on theory, where I worked on statistics and information theory before, including but not limited to robust statistics, knowledge distillation, and noisy computing. But I also see very interesting new science problems in those GenAI models, especially on how we characterize the diversity and quality of those data, and how we can learn from mixed data, when we have both access to synthetic generated data by GPT-4, which can be more biased and less variance, and also human data, which are usually much more expensive to collect, but they're usually being less biased but higher variance due to the fact that humans disagree with each other a bit more. There are also different questions like how do we do better confidence estimation of those fine-tuned networks, especially when considering this reward learning procedure where we initialize reward model from a pre-trained model, which already trained on a large-scale data set, and further fine-tune that on a relatively smaller scale data set. There are also different problems related to robustness and privacy in GenAI procedure, and also we recently have a paper that tries to formulate this watermarking problem as a hypothesis testing problem and prove the uniformly most powerful test and also minimax optimal rate for these cases. I've also been working on some different theory in bandit and reinforcement learning, where there's some new exciting work on weak to strong alignment that when your reward signal or your data is actually from a weaker source and you still want to align a stronger language model, what could be the best way to do that? And also we're exploring better serving methods with different analysis in bandit and reinforcement learning, where we have a recent paper that tries to prove the regret minimax bound for those cases. I also have some work on game theory in terms of contract theory and stackable game, where like I see new science problem in terms of learning human preferences for different areas, including economics, game theory, and human-AI interactions, and also how we can utilize the insights to improve the reasoning, planning, and interactions in AI agents. So in a short summary, I'm mostly working on statistics, information theory, and language models. And essentially, my recent work has been dedicated into improving the efficiency of the model training and serving, and also improving the autonomy in terms of function calling and tool uses or reasoning and planning capability of small models. And furthermore, I'm looking at the security problem, where we have some work on watermarking, tool use safety, and also RHF and prompt injection jailbreaking. I think that's pretty much all I have for today. Thank you so much for coming, and any question will be welcome.
Do we have time for questions?
Oh.
Yeah, actually, could you say a little bit on the watermarking and just what you think about the potential for watermarking to actually work? Because obviously, unlike images, where it's very hard for a human to identify a watermark in an image, something like text, if you make a few edits, it's a much lower bitrate signal, and so for text, it might be much easier to defeat, to make a few word changes here and there and destroy the watermark.
Exactly.
And actually, as someone who regularly suspects people are using GPT on their homeworks in my classes, including last night when I was grading, I'm just wondering, like, what do you think about the watermarking as a potential solution?
That's a very good question. So there are two ways that can prevent watermarking from working. The first way is you do some simple edits by yourself. In this case, there are some important line of research that's trying to dedicate to robust watermarking. We're trying to design watermarking scheme that is robust to some level of perturbation, maybe up to half of the tokens that you see. And this also comes with, there are some work come with very good theoretical guarantee on how you can guarantee robustness in those watermarking algorithms. But there are second attack that is even harder to defend against, which is you just use an open source model to rephrase your responses. And then the response will be very different from the original response. And that part is very hard to be detected or using any watermarking algorithm to detect. But I personally believe there's still some value in studying this problem in the sense that in the future, if everyone is just simply getting some responses from GPT-4 and just directly send that to the internet, then the internet data might be just polluted. So that when you further train a new version of the language model, you don't know whether this data is from your current model or from human. So to prevent this from happening, where people won't be rephrasing, but directly sending the content to the internet, then watermarking idea might still be applicable, or different robust watermarking idea might still be relevant in this case. And it's mostly designed to prevent the first case I mentioned here. And for this rephrasing case, I think it's still a very hard open problem how we can design watermarking to guard against these cases. Yeah.
So I've got a lot of questions, but how much time is there?
Yeah, we still have like 10 minutes.
10 minutes. Okay. So other folks should ask questions too. So just the whole idea of RLHF, right? That you actually need to learn a reward model, and then you have the challenge of the reward model learning in the first place. On the one hand, you could say maybe it's somewhat analogous to the benefits of distillation, that maybe it's better to train one model with another model. That's, maybe some noise or some properties that are bad about the data can be smoothed over by the reward model. So there's some theoretical things that you can show. But at the same time, it's very indirect. And and there's the paper that just came out of Stanford that you're aware of that, just trains the policy directly without actually needing to go indirect through a reward model. And so, since this is a high-level talk, maybe you can speculate about the next 10, 20 years about what approach is better. Is it better to pay the cost of having an extra reward model? It's kind of like afterbirth in some sense, that you don't really need the reward model, but it's there and you're using it, and then when you're done, you just sort of toss it away. And maybe it's better just to train directly somehow, using, for example, some method like the Stanford or some other new method that hasn't yet been developed.
That's a very good question. I think that's a very important research direction on how we can get similar performing methods that can get around reward model. And actually, our methodology of this overcoming those overfitting and overoptimization issue can also be applied directly to those DPO methods, because a key idea of DPO is trying to reparameterize those reward model with a language model, so that eventually you're directly learning a reward model using your reparameterization of language model. So as you can imagine, since they're also doing reward model learning, so they also face this overfitting issue. And people did observe in practice that you can only train for one epoch. And usually that's a best sweet point. You have to stop your DPO as well. So with this idea of iterative data smoothing, you can also update your labels accordingly and using similar idea to actually prevent DPO from overfitting. But in our experiments, we did try to compare both PPO and DPO in this case. And we did find that it seems that in our limited experiments that PPO still have an advantage. And my personal guess in this case is that the formulation of DPO is using a method called reward-weighted regression. And in reinforcement learning, there's another method that is advantage-weighted regression, which is actually trying to look at advantage of all the intermediate tokens and claim that to be the objective. And DPO is using a different objective of reward-weighted like regression, where we did find that usually AWR can work better than like RWR. And in PPO, we really go with AWR, with generalized advantage estimation. So that's one reason I believe maybe there's like PPO still stand the benefit. But I believe that if we can further like slightly improve the method to take advantage into consideration during the whole training procedure, it's likely that we can also get around reward training. So that's a very important and exciting future work that we can push for. Hope this answers your question. And happy to discuss more offline as well.
Could you comment more on your thoughts about weak to strong alignment? You said you're working on that as future work. Do you have anything in the pipeline that you're looking for?
Yeah, that's a very good question. So we feel like this problem is actually also very similar to the problem where we try to learn from mixed data, especially when we have synthetic and human data. So usually the weak to strong alignment problem is assuming that maybe we have very limited capability to label those responses that are too strong or like too complicated. Like if I have a code base with 100K lines of code, then it's very hard for people to read through that and tell me like whether this code base is better than the other one. So that's a scenario where you can only get very limited data, but those data might be very high quality. And in my case, it might be a human data. It might be called a human data, which is very small in scale, but you believe that it's unbiased and very high quality. But on the other hand, you might have some very simple, large-scale synthetic data that might be generated by existing language model like GPT-4. And so they are not perfect, but in most of the cases, it might give you some signal. And the question is similar in this sense that we can still design some good statistical estimators using both high-quality data set, but very small scale data set, combined with some like low-quality data set that is synthetic, that might have larger bias, but we know something might be good for those data sets. So it's mostly, I believe, the whole, or like the ultimate picture of this weak to strong alignment might also be we collecting very small scale data set from experts, and then we use this signal combined with large scale synthetic data to actually finish this weak to strong alignment or improve a stronger model.
Question? So you talked briefly about building like open source data sets for training these large language models. But a lot of times, as you were just saying, a lot of times, that's going to be off policy data. And I've seen some evidence that if you are using these off policy responses to train these LLMs, performance actually dramatically decreases versus if you're using even a poor teacher but generating on policy, evaluating on policy responses. What do you think is the future in the next few years? Are we going to be moving to a world in which everyone's going to be using large ImageNet style open source data sets to refine and fine tune these models, or is there always going to be some component of on policy generation to fine tune these models?
That's a very good question. So first of all, like in our cases, we are already trying to improving the best existing 7B chat model. So that's a case where if you have very poor teacher model, it probably won't be so helpful because the model itself is already so strong. So you do need some very strong sources of like labeling or ranking to actually further improve the model responses. And for your comments on like how good those, like whether we need like offline, large scale offline data set or an online data set, I would say it relatively depends on the availability of the data. Because usually if you query human to try to generate more comparison data set, the whole procedure can be very like time consuming. Since most of my prompt might be several hundred words, and each of my response might also be several hundred words. So even for human to read all the responses and rank them, it might take 5 minutes for a human to finish. So that's why usually you have to do that in offline fashion at this point. But if you're okay with like more automatic way of labeling those ranking, like if you're fine with GPT-4 labeling the ranking, then it's likely that we can use some active learning idea to actually further improve the model by collecting the data on the fly using active learning idea. So I can imagine that what people in proprietary models or in these days they're using a mixture of both, where they first do single round RLHF, and based on those, like the current model policies performance, they're trying to generate new responses using the existing model and train a new reward model, and further fine-tune that using a second round RLHF. So it's like offline in each round, but then within, like in between round, it will be active learning. So I believe that might be a good combination of both. So that might be more closer to what future people would do if they really want to train a very strong language model. Hope this answers your question.
My question is also about the comparison between two viewpoints. And as you mentioned, so for simplicity, you take the whole response as the action, but you say the real action from a MDP perspective should be a token. So as far as I know, the methods like DPO, the formulation really take the whole response as one action. But the methods like PPO, because it's from the RL that takes MDP, so that in that method, the action is one token. So I'm wondering, what's your opinion about this MDP formulation versus bandit formulation? Are they essentially the same, or they have like a lot of difference?
That's a very good question. So that's why I was saying, like, in my opinion, maybe advantage-weighted regression might be better than reward-weighted regression, in the sense that imagine that if you have long responses, it's not that every token generated having the same contribution to your response. There will always be some tokens that are so important, like a yes or no question. This yes and no might just determine actually like how you explain those stuff. So we probably want to give higher reward or advantage or kind of like credit for those important tokens versus some other tokens. So that's why I feel usually it's better to actually decompose this reward signal for the whole generation into the advantage estimation for each intermediate tokens. So philosophically, I personally feel that this might be more promising in some sense. And that's also, I want to add one sentence that this is also related to robotics world, where usually we operate with this sparse reward signal. And then what you do is through like reinforcement learning, where we decompose those sparse reward signal into intermediate advantage. So I think similar story might still apply to language model as well.
Were there any other questions for Bonghua? Cool. Well, then thank you so much for the talk. Can we give him a big round of applause?